20 past. And
okay,
I'll just say, I'll do some fillers, don't worry.
Okay, no, it's fine. I just didn't, I had it on mute.
Oh, okay, no. So but let me introduce you. Sorry.
I'm ready when you.
Okay, very good. So welcome everyone to the second session of the day. Very exciting session, very filled with black holes, all sorts of exciting things about black holes. And I'm very happy to introduce the first speaker of the session, who is Samir Murthy for King's College London, who will tell us about black holes in ADS5 and phases of 4D super Yang-Mills. Go ahead, Samir.
Thank you very much. Thanks for the invitation and for the nice organization of this conference. My title is Black Holes in ADS5 and Phases of Four-Dimensional Super Yang-Mills Theory. To set the context, let's consider the prototype ADS-CFT example, n equal to 4 Super Yang-Mills theory with SUN gauge group on a 3-sphere S3 times time, and the gravitational dual, which is type 2 string theory, type 2B string theory, on a space which is asymptotically ADS5 times S5, with conformal boundary, which is the same S3 times time. Setting the ADS length scale to 1, the Newton's constant is 1 over n squared. Now, this 5-dimensional gravitational theory has a black hole solution which preserves 2 of the 32 supercharges of the theory. And this black hole, the horizon of the black hole is weakly curved. So it's big in the sense that the area and therefore the entropy scales as n square in the gauge theory units when n becomes large. And the first question we ask ourselves is, can we account for the statistical origin of this black hole entropy? So natural place to look is the 116 ppm states in the dual Yang-Mills theory, which are counted with weighted by the fermion number and some charges by the so-called superconformal index. And I'll make this more precise shortly. And so the question now is, if the log of the index, the free energy, does that have the same n square scaling as predicted by the existence of the black hole? So this question was first developed and posed in these nice papers. And at that time, the answer seemed to be no. And in the last 3 years, there's been new progress. And now we understand that not only is there an n square scaling, but in fact, we can extract the black hole entropy on the nose, including all the numbers at large n, from the superconformal index. And in doing so, we understand new things both about the gravity as well as about the gauge theory. So I'll keep this n equal to 4 as a running example throughout the talk. But of course, the question is more general. It can be posed in any minimally supersymmetric conformal field theory with some large n dual. The only difference now is that the theory has 8 supercharges, so the black holes and the states are 1/4 BPS. So first, I want to explain a little bit the meaning of this question. Okay, what is this index, and what do we expect here? Well, so the n equal to 1 superconformal algebra has a U1 R symmetry. The charge is called Q. And S3 has 2 angular momenta, of which we'll only consider the diagonal J. So the superconformal index is like a Witten index, trace minus 1 to the F, times some operator which commutes with the supersymmetry which defines that index. And the simplest case is just 2J plus Q times the parameter tau. This can be refined by adding more operators, but in fact, all the statements I'll make can be illustrated with this simple index, and I'll only stick to this today for simplicity. Now, you can do a Fourier expansion in tau, and that defines the microcanonical indices. Here, this 3 comes from n equal to 4 super Yang-Mills, where the R charge is quantized in units of a third. On the other side, you have ADS5 supergravity with a metric and a gauge field whose electric charge is this Q, and the black holes have the same charges. And now in this context, it's useful to scale out Newton's constant. So to define the small charges, J1, J2, and Q. And as before, we'll stick to the diagonal J. So you have J and Q. But in fact, they're not independent. Supersymmetry imposes a relation, nonlinear relation between them on the solution. And therefore, the black hole entropy, which a priori is a function of those 2 charges, it can be written as a function of one combination, which you can choose to be precisely the same n as over here. Okay. So here you have a sequence of integers. This is a smooth function. And the main question is, does the sequence of the log of these integers approach this entropy function asymptotically. Okay, so here is the entropy function as a function of the charge. You see it grows as a function of the charge, but also as a function of the rank in this direction. Now, what's the meaning of this asymptotic symbol? Well, there are two meanings which people ascribe to this. One is the large N limit, where the charge and the rank goes to infinity, keeping the gravitational charge fixed. This is the regime in which the black hole lives. The other one is the Cardi-like limit, where you hold fixed the rank or the theory and just scale the charge to infinity. Okay, we'll discuss both of these as we go along. So this is the index, this is the entropy. And now I want to tell you a little bit about the index explicitly. So here's the canonical index. It's written as an integral over unitary matrices of size n of an exponential of an infinite series, which is controlled by this so-called single letter index. Okay, that's the same trace as defined as the one that defines the index, but on the space of single letters, namely just the fields and the derivatives of the theory at one point. And this exponential then collects the letters into supersymmetric words, and then the integral projects onto the gauge invariant subspace. Okay, so now, as usual, if you want to calculate such integrals, you diagonalize the matrix, and because U is unitary, the small ui live on a circle. Okay, let's say they go between 0 and 1. These are eigenangles or eigenphases. And when you write the invariant Haar measure in terms of the flat measure of the eigenvalues, you pick up some van der Waals determinant, which is a two-particle interaction in the space of eigenvalues. And now notice that the original action itself is also a two-particle interaction. There's only trace U, dagger. And therefore, the whole action, the whole integral, can be written as an integral over n eigenvalues of an action, which is only which is a sum over pairs of eigenvalues with a potential depending only on the difference. Okay. So here I've written explicitly the single letter index for n equal 4 superangles. So you can write the potential explicitly as well in terms of some infinite product. Okay, this is a very nice function. There's lots to say about that, but I won't because of time. I just want to show that this is completely explicit. So now we have both sides of the problem, the first question completely well defined. So we can study this on a computer. So here are some results. So this is the x-axis is the charge, and the y-axis, the solid line is the black hole entropy formula, and these dots are the logarithm of the absolute value of the microcanonical index. Okay, and you see that even for very low rank, this is U2, U3, U4, etc., there's a remarkable agreement between these two. Then you begin to see some patterns. There are oscillations, which you see better here. Okay, and then at very small values of charge, something else happens. So all of these things are to be discussed. I'll make some comments about them. But the main question is, can we understand, can we explain this agreement from a theoretical point of view, analytically? Okay, and in order to do that, instead of considering the sequence of integers, it's useful to consider the canonical index, the generating function. Okay, so that's where we'll go next. In fact, in the ADS context, the masters of black hole thermodynamics had already taught that it's natural to consider the canonical ensemble. If you fix the temperature and the chemical potentials, then the black hole is some finite energy localized excitation in the bulk because of the gravitational well in ADS. And in this context, the basic ADS-CFT equation is an equality between the partition functions, okay, with the usual map of parameters. Now, the gauge theory partition function is defined, as usual, as a thermal trace, which informs us about the microcanonical degeneracies. On the gravitational side, we do not have a Hilbert space understanding, and instead we take a path integral and try to write it as a sum over saddle points. Okay, saddle in the large N context means solution to the equation of motion. And at each saddle, you write the exponential of some effective action. And as Gibbons and Hawking taught us, after appropriately regularizing that action, that should be interpreted as the free energy of that saddle or of that phase of the theory. And we know some phases. We know empty ADS, this is the ADS black hole, and there can be many others which we don't know about. Okay, so these are two completely different ways of understanding the same thing. And in this beautiful paper of Witten, he explained how to understand these saddles or phases from the gauge theory ensemble. and in particular, how to understand the Hawking-Page phase transition as the deconfinement transition in gauge theory. Okay. So now we want to take this as a template, and now we want to apply this to our supersymmetric problem in a hope to do better. Okay, we want to be more precise and get more details. Okay. Now, when you try to do that, there is a conceptual problem that hits you. So people ask, why should the index be equal to the entropy? Okay, so here are my thoughts. Here's the index defined in gauge theory, trace with a minus 1 to the f. Now, by the usual Feynman understanding of quantum field theory, this trace is a path integral over gauge theory over S3 times S1, where the S1 is fibered with this parameter tau, and the fermions have supersymmetric conditions around the circle. Now, by our understanding of AdS-CFT, this path integral should be a path integral in the gravitational theory, whose boundary conditions are set by the same S3 times S1. And now the fermion, the gravitational fermion, the gravitini, should have supersymmetric conditions around the circle. Okay, so this is some gravitational version of the index. And the question is, does the supersymmetric black hole contribute to this index, okay, as a saddle point? Now, this is a subtle question because the Euclidean version of the supersymmetric black hole has a divergence. It's because of the fact that in the interior of ADS, instead of capping off with the horizon, there's an infinite throat. And relatedly, the temperature and chemical potentials all get frozen. So the usual Gibbons-Hawking procedure is singular. Okay. So the technical question is, can we regularize this solution and the associated products? So in order to do so, we have to sort of extend our solution space. So there's actually a known 4-parameter family of solutions which are not PPS, 2 angular momenta, a mass and a charge. And in this space, there's a one codimension surface of extremal solutions when the horizons approach each other, and another codimension 1 surface of supersymmetric solutions where the mass and charge are related. Okay, and our black hole lives here at the intersection. And over here, you can check that all the potential, this is the temperature, chemical potential for the charge, and this is for the angular momentum. They all got frozen. These are values in Planck units independent of the charges. Okay. So clearly what you have to do is to get out of this point and then approach it as a limit. Okay. And if you want to maintain a supersymmetry, then manifest supersymmetry, you do it in the horizontal direction. So this is what we did here. So you go here, and over here you redefine the new, so redefined chemical potentials. So beta goes to infinity, omega minus omega star goes to 0, such that the small omega and phi for angular momentum and electric charge, these are finite. And when you measure these potentials somewhere here, you find that they're related as such. Okay. Now, what are the solutions over here? The solutions in the Lorentzian theory are not physical. They have closed time-like curves. But in the Euclidean theory, they're perfectly well defined. They're regular solutions, except, well, with one property, that they're complex. Okay. So here I've taken a real slice, and then there's a perfectly regular cigar-like solution with a capped horizon. And these are supersymmetric. And I should make one comment that on the cigar, there's only one spin structure allowed for the fermions, which is antiperiodic. But in fact, the solution has a holonomy of the R-symmetry gauge field such that when you take the fermion and transport it around the circle, it actually picks up a phase of +1. Okay, so these are supersymmetric, and therefore they contribute to this gravitational index. And now the question is how much? And now you can run the Gibbons-Hawking procedure because everything is well defined. So in terms of these redefined chemical potentials, you can calculate the on-shell action with the appropriate regularization. Okay, then you have to take a limit as beta goes to 0, but happily, this action is actually independent of beta, as you might expect from supersymmetry. So omega is 2 pi I tau, and with that notation, the free energy of the black hole, the on-shell action, is the following. It's pi I n squared over 27 times a cubic function here divided by a quadratic function. Okay. This function we'll see again and again in the following. Okay. So one point is that I want to re-emphasize that these solutions are complex, and we really don't understand all the rules of AdS-CFT with complex sources, especially at subleading orders in n. And there's some nice progress on this in a recent paper. Okay, now what have we achieved? So what we've done is to recast this question of Bekenstein and Hawking of whether this sequence of integers approaches this thermodynamic entropy to a question of ADS-CFT in the canonical ensemble, namely, is it true that the free energy of the black hole is asymptotically equal to the logarithm of the canonical index at some saddle point? Okay, and these two limits translate to two equivalent limits here. Okay, now the exponential growth of this sequence of integers translates in the canonical ensemble to the exponential growth of the canonical index itself. In other words, log of in has a singularity at tau equal to 0. Okay, and the saddle point lies somewhere very close to that. Okay, so that's where we'll move next. We want to study the saddle points and the singularities of this function. Okay, and now you can ask, well, why only tau equal to 0? There might be other singularities which signal other phases. Okay, so that's where we're going next. So this question of the behavior of this canonical index has been studied intensively in the last 3 years from different points of view and by different groups. And by now, we have a good picture of the answer. Okay, so let me present the answer first, and then I'll mention the methods. So we expect that the index can be written as some sum over saddles. Here's the Q plane. Q is e to the 2 pi tau over 3. And the interior of this is the unit disk, which is essentially the upper half plane in the tau variable. This function I of tau, the index, is perfectly holomorphic in the interior of the unit disk and potentially has singularities at the edge, the unit circle. Okay, and near that will lie the saddle points. Now, first we look near tau equal to 0, and there we find that in fact there is no growth. Okay, there's a bit of a surprise because of our expectation. Okay, the leading growth appears at the cube root of unity, and over there, the growth of log of in is the behavior of log of in is exactly that of the black hole free energy. Okay, so in order to study the black hole, you have to change variables tau goes to tau plus 1, and then zoom in tau goes to tau to 0. Okay, and then it was shown here that this change of variables is perfectly consistent with the ADS-CFT dictionary as applied to this complex saddle. Okay, so that's one method. Now, the second statement is that there is actually a complex conjugate saddle with the same growth as that of the black hole, but opposite phase. And in fact, at the end of the day, it's the sum of these two which provides for these oscillations that I showed you in these plots. The next statement is that, well, why only cube roots of unity? Generically, at any root of unity, there is an exponential growth of the index. There's some number theoretic condition which I'll show you in a second. So tau is a rational number minus n over m, and q is a root of unity. Okay? So these are the main statements, and I want to explain, well, just mention a little bit the methods. Okay, so first, let's zoom in towards the black hole. Okay, there we go. So remember that the index is written as this integral over eigenvalues defined by a potential, which is given by this infinite product. So as tau goes to 0, we need to do some asymptotic analysis of this infinite product. And the answer looks like this. The action, the potential, begins as 1 over tau square, then there's a 1 over tau, and then there are regular terms as tau goes to 0. Okay, so this is what the potential looks like. And therefore, all the eigenvalues in this limit, they want to clump up. They all want to clump up at one point. Okay? And then you can evaluate the saddle point value of the integral and so on. And so in the original papers, in the first papers, we studied the singular terms, the 1 over tau squared and 1 over tau and so on. And then this was extended in various directions. So apologies if I missed any paper, by the way, throughout the whole talk. Please email me later. I'll be more careful in the future. But more recently, in this nice paper, the all orders expansion, perturbation expansion, was found as tau goes to 0. Okay. And then in this paper with Arash, Arabi, Ardehali, we found the all orders expansion near every rational point. And this is what makes for this picture. There's one way to understand this picture that I just showed you. Okay. So by the way, this whole method can be done at finite n. You'll probably hear more about this in Leopoldo's talk. Okay, the second method is to directly study the matrix integral at large n, trying to use the usual large n techniques. Now, from all that I've said, it's natural that we should look for complex configurations. Now, complex here means complex in the eigenvalue plane, the U plane. Remember, originally U went from 0 to 1. This is work with Alejandro Cabo Bisset, who had this beautiful idea that we should study periodic configurations of eigenvalues. And that's because the potential is already periodic with period 1, and it's almost periodic with period tau. Okay, so we wanted to mirror that. So what we did was
5-minute warning, Samir.
Thank you. What we did was to deform the potential to make it explicitly doubly periodic. Okay. Now, with such a potential, it's very easy to show that the uniform distribution along any period is a saddle point. And therefore, you have a family of saddles labeled by m, n, which is any point on the lattice generated by 1 and tau. Now, to calculate the action of this saddle is more difficult, but we were lucky in that our deformation is very closely related to a function studied by number theorists called the Bloch-Wigner elliptic dilogarithm. And they give us a formula for the Fourier expansion of this function along the two periods. So it's a double Fourier expansion. And now if you have the Fourier series, and if you want to calculate the integral, this is not very difficult. It's essentially the average value, and so it's a 3-line calculation. Okay, so that's the sketch of the method. I should say that in the original paper with Alejandro, we had some doubly periodic extension of the potential, which was not meromorphic. And now in collaboration with mathematicians, Stavros, Garoufalidis, and Donzagier, we understand that there's also a meromorphic version of the whole story. Okay. There's also a third method called the beta ansatz method, pioneered by Benini and Milan. I won't talk about this much. I want to say that whenever we can calculate anything in more than one way and we have control over it, the answers agree. So let me show you the answer now. So we have this set of saddles labeled by m, n. Tau goes to minus n over m. So tau tilde defined here goes to 0. And in this small parameter, the effective action is the following. It's n squared pi I over 27, the cubic function divided by the quadratic function that I showed you. This chi1 here is 0 or plus or minus 1, depending on some mod 3 condition. Plus a constant term, which I won't talk about because of time, which is also very interesting. Okay, so let's focus on this. So in particular, it means that the 0, 1 saddle, the action is 0. And the 1, 0 saddle, the action is here, is this, which is precisely the free energy of the black hole. Okay? So now let me show you all this in a picture. So this is the tau plane. And you can put yourself at one point and ask, which of these infinite number of saddles dominate in magnitude? So at imaginary tau equal to infinity, it's the 0, 1, it's the pure ADS that dominates. When you go towards tau equal to 0, it's the ADS black hole that dominates. So this is the new, I've shifted tau goes to tau plus 1. This orange region is the black hole. There's this complex conjugate saddle that you see here. Here I've cut off imaginary tau at 0.1. If you go down further, you see this very beautiful and rich picture that near every rational point, there's a new saddle point, and it has its own sort of chamber of value where it dominates. Okay, it's also a very chaotic picture. And now I want to make some comments about this formula. Okay, so what we have at the moment is something like this, that the canonical index is a sum over rational two pairs of integers mn with this effective action that I just showed you. This can be extended to flavors and in other directions. I want to focus on this. Firstly, this is not an exact formula. We don't even know if these are the only saddle points. At large n, I think, well, I personally think that these are the only saddle points, but I don't have a proof yet. But even if this were the only saddle points, this is not supposed to be a convergent expansion. Instead, you think of this in the following sense. Whenever tau goes close to any of the rational points, this effective action dominates, and you have the complete perturbation expansion. Okay? So if you are in one of these chambers, you have the perturbative series of the entropy of the action, free energy, And then there are non-perturbative corrections, let's say in e to the minus 1 over tau. But if you stick to one point and then, sorry, at that point, if you first take n squared to infinity, then all these non-perturbative effects completely die. Okay, so it becomes an exact formula. In other words, inside a chamber in the larger limit, you have an exact free energy formula, and the phase boundaries become sharp. That's one comment. This clearly is a prediction for a family of gravitational solutions. I should have said something. Oh, I won't say it. Remember that the effective action had a 1 over m in it. Maybe I'll show very quickly. Here, it's a 1 over m here. And that clearly means the entropy goes down by m. That's just an orbifold. And this was understood. The solution was constructed in this recent paper. Okay, this is my last point. That quite surprisingly, every term in this expansion, this effective action, can be derived completely from the three-dimensional effective field theory. So think of this as S3 times S1 and do a Kaluza-Klein reduction on the S1. It's like a Cardi philosophy. It's not a vacuum energy, but you can write down what is the effective field theory in the 3 dimensions. And that is governed by some Chern-Simons theory. You have to integrate out all the Kaluza-Klein modes. You can do that. And what is important is both the background as well as the dynamical fields. And surprisingly, you find this full effective action, including the black hole growth, as well as all the subleading coefficients. Okay, so then that essentially finishes my time as well as my talk. I'll leave you with a summary of things that I discussed and also things that I would have liked to discuss but didn't have time. Thank you very much for your attention.
Perfect, Samir. Thank you so much. So let's react with a warm applause. So thank you. Okay, so it's perfect because it gives us a few minutes for questions. So please use the raise hand feature if you have questions for Samir. Otherwise, I'll start interrogating him. But okay, Ethan Wong, please ask your question.
Hi, Samir. Thanks for a nice talk. So just have a question about this expansion that you have in terms of the sum over this saddles. Can I understand this through some modular property of the index?
Okay, thank you very much. That's a very nice question. The answer is no, and then maybe. So, so indeed, in the last 5 years, so the first thing many people guessed was, well, maybe just like in 2 dimensions, this
yes.
one also has a modular property. But it's clear that under SL2Z, there is no modular transformation. So by modular transformation, I should make it clear. I mean that there is no automorphy property, no symmetry. Okay, there is a very interesting relation already due to Felder and Marchenko that at one point in one function is related to another function. So this was already there. That's something like a co-cycle property. So there is no, as far as we understand, modular automorphy property. However, it looks, and another way to understand it is that the effective action begins with 1 over tau square. As you know very well, modular forms begin with 1 over tau, so it cannot be an SL2Z modular. However, in this work with Alejandro, what we understood is that there is some secret modular type property underlying this, and this is because of these relations to this Bloch-Wigner function. Right. And the statement is that that this function is what is called a period function. So roughly, very roughly speaking, the lack of modularity can be controlled by another function. So we can discuss this more. But there is something, and there's work in progress with mathematicians.
And do you think this notion of this certain lack of modularity can be also generalized to other 4D-into-1 theories?
Yeah, I think if you understand this n equal to 4 theory, this is not an easy problem. If you understand this fully in n equal to 4, then generalizing it is I think, less difficult.
Okay, thank you.
Okay, next on the list, Mukund, please go ahead.
Hi, Samir. I was curious if for these other solutions you have, which are complex Euclidean solutions, is a Lorentzian causal structure understood?
I don't understand it.
So are they
short answer?
So it sounds then like we understand what solutions in the Euclidean quantum gravity path integral contribute to the entropy.
Yes.
But we don't have an interpretation in terms of some
state.
Horizon states in some horizon, or just Lorentzian geometries?
Okay, so two answers. Firstly, I agree, as you said it. And in fact, let me remind you that for CFT2 as well, it's the same thing. If you remember this Maldacena-Strominger family and this fairy tale expansion, the same thing. The two of the saddles are understood in the Lorentzian theory and the other infinite numbers are not. So I certainly don't have an understanding in terms of horizon geometries, but there is some understanding in terms of what the states are in the Yang-Mills theory itself, which is also interesting. I had no time to talk about this at all. I'm happy to discuss it.
Great. Thanks.
Okay, great. Shiraz, please go ahead.
Hi, Sami. Thanks for the really nice talk. If I understand right, the entropy that comes out of this index at charges or energies of order n squared is given by black holes, yeah. And at charges of order 1 in units of n is given by multigravitons. Mm-hmm. Do we know what the formula is for the index entropy at charges of order n or n to the 3/2?
So of course we know the formula, but I guess you mean, do we have a good sort of nice analytic expression for the?
Yeah, can you write down d of n in that region? And yeah.
So this is exactly this point. So let me say I don't have anything now, but I think this can be done. I don't know exactly whether it's n to 3/2 or not, but there is. Maybe let me just show you a picture. I had something of this sort. So this is exactly what you said. So this was my entropy plot. These are the gravitons. I can discuss this more later, but let me just go to what you said here. It is over here. So these were my entropy plots at very small charges. Over here, as you said, you understand this completely in terms of gravitons. You can see explicitly that there is an agreement with the graviton function. And then this index, which are these dots. So this red one is the graviton index. These one are Yang-Mills. So over here it agrees with graviton, then it starts increasing, and then it goes up to this black hole. This is exactly what you said. So what we understand is, analytically we understand this point. Analytically we understand the asymptotics. So this part I showed you in the talk. And now usually, so there are two expansions one can do. So either coming from up or coming from down. Going from down is something that's not been studied much. So what I understood in my paper is an analytic understanding of why or of how the index exactly equals the graviton, the index exactly equal to the graviton index up to some value of charge which is equal to 2 times n. But there's an expansion where you can start studying these deviations. Okay. So that's one possible approach. I'm just telling you whatever I know. And the other possible approach is to start from up, so and then start coming down in charge. Okay, so you can try to then do both of these and see if there's an interpolating formula. This is where things stand at the moment, but my hope is that there'll be more analytic structure to be understood here.
Okay, I think sorry, Shiraz, you wanted to. Do you have time? Oh, sorry. Okay. So let's move on to the next talk, and there will be a discussion